Hey guys, it's Steve. I'm back finally. I've got my internet upgraded. That was my biggest problem before. It took forever to upload anything. And I'm now on fiber, so I can record stuff for you and I can put it on the internet and it won't take me all day of tying up my bandwidth to share it. So hopefully I'll get my videos up and going and running once again, and it won't be another month gap in between them before you see something else from me. So I'm hoping to get back on schedule and start doing recordings a little more often for everybody. So let me start out just by apologizing for giving you such a large gap between updates. I know I promised that my next lesson was going to be in calculating mem with more than one dimension. And I've actually started to write it up. Here's my Beyond the First Dimension tutorial. As I was working on it and going through here with everything, I decided really I should cover some information with REDIM Preserve and stuff first. Uh, REDIM is one of those commands that lets you resize an array in memory, and preserve lets you preserve that array while you resize it. And yet, people who work with multi-dimensional arrays are always complaining that it corrupts their data. They don't quite understand what what the command is doing to their array. They don't quite understand it. And since we're working with memory and how everything sits and works with it, let me take a moment before I get back to calculating our offsets to talk about REDIM first, and then I'll do the next tutorial with calculating the offsets. But if you pay attention to what I tell you in this one, it'll really explain a whole lot of what's in the next one as well. Um, so I've already wrote the code for this. I shared it on the forums. People's had a little time to look it over. Uh, it by itself, I don't think the code's going to explain a whole lot to you. So I'll just take a moment and I'll explain it as I go along, and hopefully me talking about it will help you understand what I've shared. This isn't set to read from top to bottom. It's set for me to run it and explain it as we go along. But part of it I'll need to comment out and run it a couple of times to show you the differences in how things perform. Uh, but the question I asked on the forums is the same one here. How's the data stored in memory? You know, is it stored left to right, top to bottom? If you remember my lesson on Little Indian versus Big Chief, you can write your data however you want. If we take the sentence, I like cheese, well, we could write it left to right across the page. We could write it one letter on each line of the page, so it'd go top to bottom. We could write it from the right side of the page to the left side of the page, like they do in Arabic or Japanese. Well, I think Japanese is top right to bottom right, and then to the left. But what direction we write it really doesn't matter as long as we realize that we're using that same direction. Where it does come in important, though, is like with the memory or with REDIM, is how it's stored a two-dimensional array in a one-dimensional memory block. It's just written straight through. If we had an array X, Y, Z, P, D, Q, that's a six-dimensional array. Well, we don't have six-dimensional RAM chips that we can stick into our PCs and have it place it exactly like we'd imagine it in our head. It doesn't work like that. It's just stored in a spot from position 1000 to position 3000 or whatever. It fills that one section of memory, and that's all it does. So here I'm asking, how's it stored left to right, top to bottom? And let me show you a couple of different ways we could represent this. I've got an array, 3 elements for the first element, 4 elements in the second element. I make a little loop for f equals 0 to 3, the second element equals 0 to 4. F is the first element, S is the second element. We have a running total, a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. It's actually going to go to 20 because 0 to 4 is 4 elements. And 0 to 5 is 5 elements. And 4 times 5 gives us 20 as a total as we run through the loop. So we're going to start from 1 and we're going to go to 20, and we're just assigning those values to our array. But if we're looking to print those values on the screen, like say, are they left to right, right to left, bottom to top? Well, we could represent them left to right, up to down. You know, that's what this little section of code here is. Or we could display them top to bottom, left to right. Or the next page over. It's the same numbers. It's how we represent them, as long as we know how they're mapped. We can always retrieve our data from the grid. We're just changing our origin. If we're drawing an XY map with X going one way, Y going another, we're changing which direction we flip our map. Are we flipping it one way or the other way or whatever? Do we want X to be the line, the horizontal line, or do we want X to be the vertical line? Do we want it to run positive to negative or negative to positive? So how we look at it as people, it's all up to us. How we want to draw it and map it and represent it on the screen. How it's actually stored, if we want to look here, well, how the heck is it actually stored in memory? We get a mess. Well, we were counting 1, 2, 3, 4, 5, but if we look at it in memory, it's actually stored 1, 6, 11, 16, 2, 7, 12, 17, 3. This is directly calling it from memory itself. If you look down here in the code as I scroll down, we're now to this segment of the code, and this right here basically is where I'm asking just how the hell is it actually stored in memory. And if you notice in the program here, I'm missing all my Y's. All that should be always and stuff. It's because I was lazy and did a quick copy and replace. When I started out, I did a XY instead of first and second here for F and S. So I just did a copy and replace for everything. And I didn't catch that it was changing all my variables, all my comments with every Y. So my Y's became the S. But, so when you read the comments, I didn't bother to go back and change all of them. But if you're wondering why I can't spell anything at all today, that's why. I spelled it right to start with, and copy and replaced all my Y's with S's. So you'll see a lot of those in the comments. Just know that a RS is an array, and anything is anything. But before I get myself sidetracked explaining what's wrong with the comments, let's look at the program itself. The first few was just lines to show that we can represent it as a person however we want to. How does QB4 actually allocate that memory for us, though? By asking which direction. Really? It's a trick question. Like I say, it's up to us as people to represent how we want this to be displayed, how we want it. The way QB64 allocates memory and how us as people allocate it is completely different. We do it for what's convenient for us. QB64 does it in a way that's convenient for it. It's got one set of rules. The people who created the language wrote those rules, and it follows those rules. And really, what I've did at the very, very beginning of this program is I've manually overwritten the rules of QB64, the way it normally does things. I'm assigning my total by running a loop with counting the 3 as the first element, and then I'm counting the 4 as the second element. But the way QB64 actually assigns our memory when we run it, this would have been how QB64 does it. Notice that I've completely changed my operations on how I count. And if we run this, our output should now make more sense as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 20. If you see it, QB64, if you remember, in memory, tends to go right to left. So when I'm talking directions with arrays and how they're indexed, your first element is actually the one on the far right. Your second element is the one beside it. So if we had an array X and Y, like I've just wrote here, Y is the first element, X is the second element. Us, as English-speaking people, we read from left to right. We would look at this and we would say the array of X would be the first element and Y would be the second element. And if we use U-bound, for printing our upper bound here, let me show you here really fast with another little pop-up window. I'm going to have half a dozen pop-ups here in a minute, but that's fine. We could the first element U-bound replies for us is 3. The second one it replies to us is 4. This is how we think of it because we're English speaking people. We think of this as the first array element. We think of this as the second array element. But when QB64 is storing memory and allocating memory, it does it starting with the right. This would be the first one. This would be the second one. So if we actually want our totals to fall in memory and match memory, we'd start counting from what we consider the second element, and the inner loop would be the first element. So as you can see, how we think and how it thinks aren't necessarily the same. Either way, it's going to count, and as long as we pull the figures out in the order we're used to, if I always run my loops from the first loop being S, my second loop being F, my total's always going to be 1 to 20. If I reverse this, and I copy and display it and whatnot, my totals are still going to be 1 to 20. How I interact with them and how memory stores them is completely different, but it doesn't matter for us. So in some ways, for us, it doesn't make a damn what's going on behind the scenes. It's all how we organize it that's best for us to think of it in our heads. But at the same time, we need an understanding of how QB64 would store this and work with it. And in its case, it actually, arrays are indexed right to left. We think in terms of left to right, but they're indexed right to left. So what I'm saying here is with the array above, it'd be stored in memory. With the fourth, where we've got our dimension up here of 4, those values are going to be stored first, and then these values are going to be stored next. So if we looked at it, it would actually be A00 is the first one in memory. Then it's going to be a 10 in memory. Notice how the 0 to 4 would all be coming down in memory sequentially until we go all the way through the 3s, and then we get to 0, 1. So even though it looks like we're assigning it here, it's stored in memory here. And that's what we're actually seeing when we print it. Our total of 1 goes in this spot. Our total of 2, the way we're counting with the second spot. So, yes, we're doing this as the internal loop. This is here, which is 1, 2, 3, 4, 5 positions over for 2. If we look at our output, 1, 2, 3, 4, 5 positions over is 2. 5 positions over is 3. 5 more positions is 4. 5. And that's how we get our totals in here. It's how it's stored. It looks complex as it can be when we just print it and say 1, 6, 11, 16. It has us really scratching our heads and saying, what the hell? But it's from the right to the left is how the index is set. And that's what we're seeing as I represented here, from value to value to value to value. And as I close these windows I've got, we'll scroll down in the code, and I had a little end here to say that's kind of the end of the background information. Well, now we'll go along and we'll try to explain why this is important to know if it's right to left. And as our array was A to 3 to 4, this is what the original was. I just put it in here to help refresh everybody's memory. But when working with REDIM Preserve, let me just show you. I'll REDIM and I'll preserve it, and at this point I'll preserve, I'll increase the left index first. Yeah. And as we run it, I'm going to print out a 2x2 grid again. Well, not a 2x2 yet. I'm just going to print it as it looks in memory. As it looks in memory, it's exactly what it was. 1, 6, 11, 16. Just like we had it. It's exactly as it was. And here's our new zeros that we've added where we've increased the size of the array. Well, we've increased the array. There it is. So, remember the way that looked? Well, here, I'll put it up here and leave it there. And this is what it looks like in memory when we REDIM and preserve by the left index on a two-dimensional index. Here, I'm commenting that out, and I'm going to increase the index on the right index instead. And as I flip over to that page, it looks almost exactly the same. 1, 6, 11, all the numbers are like they were. There's not quite as many zeros, but that's because one had 4 elements, the other had 5 elements. So when we increase the rows, we increase this many. When we increase the columns, we increase this many. So depending on the size of our other arrays, the other elements, that's what's determining how many zeros. We're either adding a whole row or we're adding a whole column. And if we look at it, well, hell, it didn't change anything, did it? It all looks the same looking at memory directly, except it's got a few more zeros to it. Well, and that's what I'm saying down here in the comments. As you noticed, I've got another end in here. This is where I'm saying, hell, it don't look any different. And it really don't, just looking at it in memory. And the reason it doesn't look any different is when we use preserve, it takes our old memory exactly the way it was, it copies it, it makes a new a new memory block big enough to hold the new information, and it just throws it in there. It copies the old information, puts the old information directly into the new information. So all of this is lining up exactly as it lined up in the last information. And we're getting all these extra zeros on the end because this array is bigger. If we preserved it smaller, it'd copy it over just like it did before, but it'd just chop off part of it. It wouldn't have enough room to copy everything. It'd copy what it could into the new size array. So, looking at it, it doesn't look like it does much. It doesn't change much if we change the first element or the second element. But let's actually look at what it does when we start printing our index. So it looks normal. Now here's, as you can tell, I'm just hitting the space bar to skip through the previous sections, the previous sleep sections. Here's where we had our original sized array. Here's where we redimmed it and printed it. There's the extra zeros. In this case, if we add, and what I've got here, a new row, a new row, I guess, at the end of it. If I add to the right index, all my numbers match up and they look normal. 1, 2, 3, 4, 5, and here's the 0. All of these indexes are the same. I haven't corrupted my data. It's still usable. Everything's in there as it should be. But let's do this and change the inner index. And as I step back through everything, here's where it was originally. Here's where we add our extra zeros. Here's where we have what? We have a screwed up mess is what we have. What the hell? Why did we have such a screwed up mess? You can't change your indexes on this side as we change them on the other side. You can't change inner indexes, but you can change the first element. And the reason why goes all the way back to up here. This is 0, this is 1, the 0, 0 element. As I was adding it, this would be 2. And let me just go ahead and make out my chart until I fill up enough of my screen. I want to illustrate this point so I can show you what's happening a little better. There is no... Damn it. I'm doing it backwards. 1, 1. 1, 2. No. It's funny how I can do some of the complex stuff and then just get lost in the very simplest of things. So, okay. So, at this point, we're adding from the second index. It's stored in memory in this order. Um, so, A00 would be F00. This, I'm placing it, F is the first one, S is the second one. That's how we think of it. So it's very common to see people doing this. And like I say, really, in the memory, it's stored in the opposite direction. So how we look at it and how the computer looks at it's completely different. But in this case, we would have 1, 2, 3, and I guess I really should finish this out. Easiest way is just copy paste. Okay. So when we run our loop above, and it's doing this little set of code here. Let me expand my window so I can get it all on the screen at once while I'm talking about it. Well, we're running it. It's running S. S is 0. F is 0. Our total's 1. F is 0. S is 1. The total's 2. F is 0. S is 2. The total's 3. So 1, 2, 3, 4, 5. Then F becomes 1, S becomes 0. This is where it becomes 6. So if you can see how we would lay out this in memory to match our data, then, and I'll just go ahead and fill the whole thing in just to get it. How about that? 12, 14, 15, 16, 17, 18, 19. And where did I not count right? That's 119. We count from 1 to 20. So where am I leaving a number off? Somewhere I skipped a number or something. I don't care. Anyway, this kind of shows what's going on in here. It should end at 20 instead of 19. Apparently I can't count. But if we add another element on the left, what I'm calling F here, by using it down here, F and F, if we add it on this side, what we're doing is making this the next set. Then we're adding another block in here, 4-1, and so on. But REDIM Preserve doesn't automatically insert these gaps. As you've seen when I printed it and printed it on the screen, it takes the original and it copies it over for us. 1, 6, 10, 15, 2, 2, 7. It just copies it directly the way it was originally, and it leaves it in that same order. And if you look at what it's doing with our indexes here, we've got things that are jumbled, which is what we saw when I printed it before. The first couple of elements are right, but the moment it comes to this index, it doesn't leave that space in there. REDIM Preserve takes the original data, copies it over, puts it in here directly as it was. It preserves it, it saves it, but the indexes have changed. So what everything is pointing to is all jumbled up. We didn't have, you would think when we REDIM with a new element over here on the left, you would think they would all be initialized to 0. Well, it's not, because we preserved it, we copied it over. Our new elements are actually A41's going to be 5, unless it's wherever I screwed up in my counting and I'm off a number somewhere, but this is what's going on. This is what happens if we index from the left. So as we lay out the chart, you can see where these gaps are going to be, and you can see where our data is now completely corrupted. Now let's get rid of these lines, go back to the original data, which means we don't have none of this copied over yet. And let's say that I change this to add another index on the right instead, to make it A35. I REDIM it. Well, everything up to this point matches perfectly. And here's where yes, I cannot once again keep my 0s and 1s straight in my head. Once I get it wrote out, it makes sense. Once I'm trying to look at it and write it, that's it. Okay. Yeah. So here we go. We just added the new index. We copied the old information. Here's our old information. We copy it over, same as before. Well, it lines up perfectly with what it was. And these are blank 0s. So when it comes to REDIM Preserve, you can REDIM Preserve on the rightmost side of your index. You cannot REDIM Preserve on the leftmost. Anything beyond that right, the rightmost, anything beyond that is going to be adding them in here like I showed you just a little while ago. It's going to add those gaps into the index. The data is going to be in the same order but it's not going to be indexed properly for you. The only way you can preserve your original index, which is this one here, is if you change the far right element. So if you know you have to write a program with customer records, you might have a customer record that has 10 strings you need to record. The way to do it would be to have the strings be over here. They're not going to change. You need 10 pieces of information. You need name, age, sex, whatever. Those are your 10 strings that you want to collect with your array. Those you would put on the left hand side. The customer number you would put on the right. So the first customer would be this customer. The second customer would be this one, as I'm highlighting and you're following along here. Here would be my third customer, my fourth customer, my fifth customer. As I get to the sixth customer, I can just add him into the database. I'm not corrupting my data. REDIM Preserve is working perfectly the way it should. If I decide I need more information on those customers, I have to rebuild my database from scratch. I can't just copy this and paste it over because I'm throwing a new field in here. I'd be throwing that new dimension here, but REDIM Preserve just copies the original array and puts it into the new indexes. So I'd be corrupting all my data if I redimmed it on this side. If I changed it from 3 elements on this side to 4 elements. So if you kind of take a look at how it works, this is the way REDIM Preserve works. And really, as we look into mem blocks, and the reason I got to this is because it's a good way to represent it and explain it. As we look into this, our all memory is basically stored the same. If we're looking at a graphical screen that goes X to Y, it's stored, instead of, if I called this my screen data, it would be stored X to Y. Well, if my screen's a 4x5 screen, it's going to be written just like this. And let's say my screen data's 3.5, since that's what I've got drawn on the screen here and represented out for us. It would be in this order exactly the same as an array was. Your Y's are first, your X's come second. Which means that actually the way it's stored, you think of it, this is Y0, 0, this is Y0, X0. As we go to the right, Y increases. So 0, 1, 0, 2. Notice my little cursor here. As we go to the right, on a graphic screen, your Y would increase. And your X would stay the same until you get down to the next row. And that's really how two-dimensional arrays work. Three-dimensional arrays work the same way. You just start from the right and the index lays out just like I've laid it here. If I had another element from 0 to 1, well, from 0 to 1, if I had another row, we would start out, and all of these would be 0 to start with. And then, as we increase it going along, we'd have 0 1s all down through here. And then we'd come back with the next set. These would be afterwards once we get to the end. 1 0 0 and so on. So it works the same way. It goes first, second, third is how we organize our indexes. We go from right to left. So, and yes, let's go back to the original 3 4. So this is how it should work, should look. And I'm still curious about where I screwed. Here's where I screwed up. I left an element out when see, I can't. No, hell, I don't know where I screwed up. I screwed up somewhere in here. It should count from 1 to 20, and somehow I'm only counting from 1 to 19. And I've got myself baffled, but the concept of what I'm trying to say is really what's important rather than my basic arithmetic and copy skills. As y'all can tell, I can't copy from 0 to 3 worth of shit. 0 to 3, 0 to 3. Yeah. So, somewhere in here, it should have an array from 1 to 20. I've got one from 1 to 19. It's jumbled, so somewhere I screwed up. I don't know. But the concept is what I'm really trying to push to hope people will understand. We think in terms of X, Y. We think left to right. These arrays are indexed in memory from right to left. This is why when we REDIM preserve, we can add to this value, the rightmost value, and we can't add to anything beyond that. So, if you're going to REDIM and preserve only, and I can't stress it enough, only REDIM the rightmost element. If you REDIM the rightmost element in a multi-dimensional array, your data will line up because you're just adding extra columns to it. You're putting them in here and you're adding your extra columns at the end of it. If you do the others, you're throwing those gaps in here like I showed you. Your index is going to mess up. It's going to screw up your order. In memory, they're exactly the same, but the indexes that points to those spots in memory are different. And I hope I haven't confused the issue too much, but this is why we can safely REDIM preserve the last element in the array, and we preserve our data structure. And if we preserve any other element, it gets all corrupted. And hopefully, writing it out and you following along with me and seeing the way it would preserve it and copy it over helps understand. Sometimes I think I just get myself confused trying to talk about it. It's not the simplest of things. I can't even write them down in a top-down order without screwing it up. So for anybody having trouble with it, I absolutely understand your heartbreak. I can understand for your frustration and whatnot. Once you work with it a few times and you realize that very simple rule, it's not so hard to deal with. But our final rule, and I'll put this in all caps, only, and let's emphasize that for you, only redeem the rightmost index when using REDIM Preserve. If you stick to that rule, you won't have any problems with your data. If you need to redeem in the other direction, you're going to want to do it the old-fashioned way. And what would be the old-fashioned way? It'd be to make a whole new array. Dim a temp array 4-4. Remember the old array, if I look up here, is 3-4. This was the original array, just copy it. So our original array was 3-4. I would need a temp array of 4-4, and then I'd need that for loop for x, and then I'd need a for y, and I would just temp xy equals axy. I'd have to store my information first so I can save it. Then I can use the new array. Because REDIM Preserve doesn't throw those gaps in it for us. All it does is take our existing data, copy it. It preserves it. It copies it exactly as it exists, and it puts it over in the new mem block, whatever it is that we define for it. So when we change our indexes to add that extra row, it all gets corrupted. So you may have to manually move your data yourself to keep your indexes straight. And that's what we've been seeing with this little demo and what I've tried to point out. So our final rule, like I say, is only redim the rightmost index when using REDIM Preserve. If you need to redim any other index, you'll have to do it manually. That's the rule right there, working with REDIM Preserve. And hopefully I haven't murkied up the issue too much. Hopefully you'll be able to understand the concept of why. It's how it's stored in memory and how we're interacting with it through memory. One, all we're doing is adding to the end of the array when we resize it. The other one, we're changing the inner structure of the array, and that corrupts the data. So stick to the final rule here, and you won't have any problem with REDIM Preserve. The wiki should really stress this one rule. I don't know if it does. If it doesn't, it should. So maybe somebody with wiki editing capabilities will change that. I've got wiki editing capabilities for the QB64 forums, but I'd have to hunt down my login and find it. I don't use it. I'm not a regular editor of the wiki, so it's just a hassle for me. If somebody else out there sees this, then perhaps they can go in and make those changes without me needing to. But this is the main rule when working with REDIM Preserve right here, what I've got highlighted. You can only successfully change the rightmost index. If you change any other, you're corrupting your data as soon as it reaches the index you've changed. You're changing where it points to. The data's corrupted. And that's really all there is to it, guys. And if you follow along with how it works up here, let me go ahead and switch over to my tutorial with Beyond the First Dimension. Really, after covering all of this, I think I could pretty much skip a lot of it. We'll go ahead and merge this with the other tutorial I had planned. And here is where I was talking about Beyond the First Dimension. Well, these are the formulas you would basically want to work with. As I was saying, on the screen offset is X and Y. X going across, Y going up and down. Well, it's stored in memory from the rightmost to the left elements. So in this case, the width would be our X as we go across the screen. So 0 starts out on the left in text. I suppose this however far it goes. 80 would normally be how far it goes on the right on a text screen. So it'd be 0 to 80 going rightward. Going down, we can see 1 to 21 is how many lines I've got going down. So it's stored in memory Y and then X, which is actually the same way we read it, just it's not how we think of it because we think first, second, but it's first from the right and then second is from the left. So to get your memory offset, it's Y times width. How wide is our screen? If our screen is only 10 pixels wide, that's how far you go with Y. That's how far the width goes. So this would be 0, 1, 0, 2, 3, 4, 5, so on, so on. The Y would not change, the X changes. So that's what we're seeing with the formula here. And when we come to an offset of any array, it's the same thing, only you have to go with your innermost, which in this case would be the X size. This would be the same thing as the width. It's how many rows we have. So I put this one in here just as a comment for myself. And I really haven't worked up a 3D option yet. I was going to do that, but these are the two main formulas people would need when dealing with an array of A, which is what I had up here before, an array of A. When we get to it, it's Y times the number of elements, and that's all this represents, the number of elements in the left dimension. So it's y times that number, y times the number of elements, and then plus x. And that's what we see here with width. The width on the screen is the number of elements in x. We dim our screen, we dim new image if I did this, and I can't between things, but dim a new image, 640, 480, and 32-bit. To find by offset, it's going to be a width of 640 because the 640 by 480 represents that two-dimensional array in memory. So what I've been covering with REDIM and preserve is directly the same thing that works with memget, and memput. Mem works directly with those indexes, first, second, and third, just like I was pointing out. So the main thing you really need is these two little functions to work with finding your directions with memory with a two-dimensional array. With a third-dimensional array, it's a little more complex, or fourth-dimensional, because it's all wrote one after another, but it's the same basic principle. It's a little more math involved, and there's probably people on the forums who are much better at the math than I am, and they can convert two-dimensional, three-dimensional into one-dimensional representations for you much better than I can. But the thing to remember is it's basically right to left is how these are indexed. So if you sit down and you write it out on a piece of paper, that's how they'd go, and that's how it'd map out, and that's what we see here. Graphically, it's y times width plus x. Now, one important thing, since I am talking about your graphics, to remember would be the element size in memory too. Don't forget to multiply by your element size. A text screen has 2 bytes per memory, so you'd have to move over. This would find the number of offsets, but in a text screen you would have to move 2 bytes because there's 2 bytes of information for each pixel that's on the screen. In a 256 color mode screen, your element size is only 1. And in a 32-bit screen, the element size is 4. So you have to change it by your element size. And if you look in my actual program where I scrolled up, that's what I was doing up here. Your screen offset, whatever it is, times the element size, plus where it starts in memory. M.offset is always where it starts. Your memory block offset is where it starts, and then we just move it to the right to the spot where we want. Now, setting up a function like this and using width and such things, I really don't recommend. The point of the mem commands is for speed. So this isn't going to be very fast. There's overhead in calling a function. QB64 has to call out. It does some error checking. It sees if there's any problems. And then it'd have to look up width. And it'd plug it into the formula. The best bet would actually be up here, instead of calling it like that, to plug in the numbers manually. And I don't know what I said. I said something weird. Yeah, 793 for my width. And there we would go. That would be much faster than this. They're going to give us the same number, but there's overhead associated with using a function. It's just the way it works out. And we could actually reduce all of this quite a bit. Here I know I'm working with 32-bit screens, so if I make my X's 4 times bigger and my Y's 4 times bigger, I no longer have to move it by element size. Well, because I've took that into consideration here. I've now manually made where I'm going bigger, so I've took that operation out. My X is 4 times bigger, my Y's are 4 times bigger. Well, they're not because I didn't copy it, but it should be. Where this is times 4 here, instead of calculating it as I had it, instead of calculating it, remember in math, our distributive property says we can distribute this to both sides here. So if our X's are that much bigger and our Y's are that much bigger, then we don't have to do that inside the loop. Here we only do it once, and we can take it out of the loop, and we're going to speed up our processing. We're going to speed up how quickly we calculate it. Well, this is all well and good, but can't we, by the same nature, improve it even faster by starting at our offset? Then we don't even have to add it here. If you see my point, we can pre-calculate a whole lot of these figures, and we can take them out so that what we're actually calculating with the intersection of the loop would be a much smaller number. Less work, less math. It's going to be a lot faster. The more complicated we make our formulas inside MEM, the more math it has to do, the more calculations, the slower it's going to be. Most people choose MEM for the speed involved. It's not really chosen for the simplicity. So the more you can move your math out of the inner loop, and of course this is the inner loop with my 4 next here, the more you can move your math out of this loop, the faster it's going to run in your program. So by moving my element size out, what I had up here originally did a lot of looking up It calculated a lot of things. We started at the offset. We moved into a function, so we had to pass variables into the function. We had to get an answer. We had to look up width. We had to get an answer. We had to put it in a variable. We returned it. We took that return value. We multiplied it. Oh, first we had to look up what element size is. Then we multiplied it out. And we added it to that starting offset. And that's a lot of steps that are going on right here with this calculation. Here, we've took a lot of that out. We're no longer making the function call. We no longer have the overhead. We've plugged in the numbers manually. We've changed our element size up top. So it's only calculated once outside the loop. Everything here is going to be so much faster than it was here, because we have less math to work with. And that's kind of the point, but it's really not point of this tutorial. That's just part of optimizing your memory blocks. Optimize them to take as much math out of them as possible. And if I revert all these changes, I can show you my little demo that I was working on writing up. Of course, how many times do I have to back up to erase everything? Yeah. Okay, this looks like this was more or less my original work. Now, so for this, which was going to be the start for the tutorial beyond the first dimension, it works just like what I was telling you previously. We take our memory block, our array, an array of 24 elements and 33 elements. Remember, it starts at 0, and 0 to 23 is 24, and 0 to 32 is 33 elements. So, when we want to set a value, the third element, the seventh element, we can do it the old-fashioned way, just use the array, and that's what I'm doing here. I'm just using the array to set a couple of values. And to show where we're getting it from, I used the offset function which I built, which really I did just, like I say, to highlight how you to calculate where that offset would go. And it's like I was saying with the REDIM preserve and everything else. Starts on the right, y times x size, the number of elements in x. And this isn't the quickest way to calculate this. This is looking up functions, adding numbers, subtracting numbers. The much better way would be to plug this in manually and just look at it like I did up front. Well, I got a array from 0 to 23. It would be 24 elements. The only problem is this is a redeemable array, so it may change. The size of it may change in memory, so I'd actually have to calculate the number of elements because they may change. It's not a set number. I can't just plug in a set number with a redeemable array. The array size might change, so I need to calculate it. And that's upper bound and lower bound. And it's the first element with the U-bound command. It goes from left to right because that's how we think. It's left to right. The U-bound command was made to seem natural for us, even though internally the memory's actually going, Y is the first element that it indexes by, and X is the second. But, so, how we think natively and how the computer thinks is two different things. And that's where people get lost a whole lot. But the offset, it's as simple as calculating it here. And that's what you see when I run the memget. It just puts it, I'm getting the offsets that I just put out. I never assigned anything to the variable L, my long variable. So I just get from this offset in memory my long variable, and I print it to the screen, and you see we're printing what we assigned. So those formulas hold true. They work. It's better if we don't use them as a function and plug them in manually. The less function calls, the less math and stuff we can take out, the better. But it's how you calculate that offset. It's the right times the number of elements in the left, and for three-dimensional arrays, it's the same thing. You just expanded another step over, and you sort it out as you go along. Then when we get to the screen graphics, here I'm putting things in a X, Y. One is just green dots and the other is red dots. And if you notice, to make it pretty, I had a toggle in here, if X is less than Y. So instead of drawing a line, like what we'd normally see with a square, 100 to 200, 100 to 200, I used memput to put the information on the screen, if you follow my cursor from down here up here, to make a pretty little red and green box for us. And that's what this is. So it's putting it exactly where I wanted it to go in memory. It's calculating the proper offsets. And the reason it's doing that is just from that simple formula. Like I've been saying all along, Y times width plus X. It's the exact same thing with an array. Your screen images are nothing more than a two-dimensional array stored in memory. This is how a two-dimensional array is stored. This is how screen memory is stored. As you can see, these two formulas are exactly the same. X size up here is the width, the number of elements in X. Down here, the width is the number of elements in X. That's how wide X would be. Y would be the height. So it's the exact same in either way. So that's really all it takes to work with multi-dimensional arrays. And it's also why I kind of sidestepped this lesson to go into REDIM Preserve, even though I kind of added this lesson to start with too, added it to it as well. So, but that's what you're looking for to get your offsets in memory. That's why REDIM Preserve works the way it does. And hopefully I haven't muckied up and murked up the waters too much and confused anybody. If anyone has any questions, post them on the forums for me. Post them on the bottom of the video as a comment if you want. Whatever you need, let me know where I may have confused you or where you're having issues, and I'll try to help somebody sort it out. It sounds complicated when you're looking behind the scenes, so a lot of folks mainly might need to know this, and they may need to know the highlighted version of where I highlighted the final rule for REDIM Preserve. You may not need to know everything that's going on internally and behind the scenes, but I wanted to cover it to explain why this works. After you've got it and you know why it works, most of us can look at this and forget about it. Say, yeah, okay, I remember hearing about that in the past. I understand it works. He proved it to me. He showed it to me. I understand. But it's not something I work with every day. I don't need to remember this. But what you do need to remember are these formulas. You need to remember right to left for calculating your offsets. So the offset of a screen, y times width plus x. The offset of a two-dimensional array, y times the number of elements in x plus x. When redimming and using preserve to redim and preserve your data, you can only redim and preserve the rightmost index. Right to left. If you start changing anything to the left, you corrupt your indexes. You have to manually redim it and preserve your data, because all it does is copy and paste. Redim preserve is just a copy and paste of the data over. And in most cases, and for most people, it works. Most of us work with one-dimensional arrays, and if you structure your data knowing how it's going to be affected, you can redim and preserve two-dimensional arrays, such as I was talking about customer numbers and a certain amount of information. The order of which you preserve will affect whether you can use redim and preserve or not. If the data is set but the customer numbers aren't, then you want the customer numbers to be on the right. If you've only got 10 customers, or say your family, if you've only got your family, you know your wife and how many children you got. You should keep that on the right hand side, and over time you might add new information for them, like a list of things my wife likes, the things my family likes. Well, you've got 3 family members, and you may need to redim and preserve it to increase your list of things you learn about your wife that she likes or doesn't like. So how you structure your data is really important when using redim preserve, because you can only redim the rightmost element. Anything else corrupts the index. So keep that in mind when working with redim and preserve. But when looking for offsets for use with mem, right there is the formulas. It doesn't actually change in memory. It's set up. These are set formulas. This formula will never change. When you want to get an offset of any screen mode, it's y times width plus x. But remember, that's just the offset to tell you how many positions to move. You also need to know, like up here, what the element size is. So depending on your screen mode, text screens are 2, screen 12 or screen 13, which are 256 color modes. Those are only one element size. 32-bit screens are 4 bytes of information for each element. So this tells you how many elements you need to move over in your array, but at the same time, you got to know how big those elements are, and that's what I'm calculating up here. I didn't want to put it down here because depending on how you do your math, you may not always need to calculate that. Like say, if I've moved these numbers, my element size, into my 4 loops, already distributed it across into my X and Y's, I wouldn't even have to calculate it inside the innermost loop. So I'd already have that accounted for. So the key formula is y times width plus x for a graphical screen, y times number of elements in x plus x for a two-dimensional array. And really, like I say, that's all a screen is. It's a two-dimensional array of information in memory. It just starts at m dot offset. So it's wherever it's at in memory. I don't know. I don't know what m dot offset is. The computer tracks where it stores it in memory. It finds a nice safe spot and it puts it up there, and this is where we access it as the very first byte. And that's what it is to it. And like I say, if I've confused anyone or got complicated, just post me some questions, ask me about it, send me an email, whatever you need, and I'll do what I can to try to help sort things out. But hopefully, I haven't confused you more than I have enlightened you. uh, I have issues myself with some of this stuff. My brain knows how it works, but it's like when I was trying to type in the screen, I can't type from 1 to 5 or 1 to 3, whatever the hell my elements were. I couldn't get a count to go from 1 to 20. And where I was wrong with that, I don't know. And later I might go back and check the video and say, where the hell did I screw up? But somewhere I screwed up, but it don't matter. But the concept is what I was hoping to impart to everybody. So I think this is going to wrap it up for our video. I tend to ramble too much. You guys probably already learned that by now. But hopefully I can get something else up for you before too much longer, within a week or two. Looks like this will probably be a fairly large video. I'll probably leave it like I did the last one for a couple of weeks. Give people time to look at it, digest it, view it, and ask me any questions. And then I'll go on. And I suppose the next lesson will be, like I was talking earlier, a little bit about how to optimize how we interact with MEM. We've now figured out how to find the offsets. Well, let's talk about optimizing them later into finding them in the most efficient manner we can to speed up our programs, because that's the whole point of MEM to start with, to speed up our programs. So in the future, we need to talk about optimizing MEM. Then we need to talk about a few more of the key steps of MEM that I haven't covered. M dot size tells you the size of your MEM block. M dot element size tells you the size of each element inside the block. Well, there's also a M dot type. I haven't seen anybody else on the forums use m.type for anything, and it's a truly, truly powerful feature of mem. Once people get used to it and realize what it does for us, it throws a whole new level of power to the command. So look forward to when I start talking about m.type. Hopefully we can get people where they don't feel frightened by it and they understand what it is and how it works and understand its purpose. So that's going to be in a future tutorial as well. But at this point I'm going to wrap up today's. Hopefully I'll hear back from some of you guys. And if everything goes well and we continue along, we'll have another tutorial in a few weeks. Good luck, guys. Bye.